First of all, it's a differential equation because I have a derivative and an equal sign. That's all it takes. Next, I'm looking at the variable in the numerator is x. Since only x appears over here, I know that it's autonomous. So now I'm asking myself, well, if I have to solve the thing, I sure hope it's separable. There are two different ways that we can go about separating this. I'm going to go with, well, whatever, I'll show you what I'm going to go with. So I'm going to start the way that I always start one of these separable ones, which is since we've got the dx dt isolated, I'm going to multiply both sides by dt. So over here, now I have dx is equal to 3 minus 2x dt. And then I'm going to look at this side and say, I know with that dt, I only want to see t's over here, not x's. I'm going to divide both sides by this entire thing. The other option would be to factor a number out, but I'm not going to worry about that. I'm just going to divide by 3 minus 2x on both sides. So on the right-hand side, I'm secretly left with 1 dt. And on the left-hand side, I'm going to go ahead and separate that out to look like 3 minus 2x dx. And now I'm ready to find the antiderivative on both sides. On the left-hand side, we can use a u substitution, or if you kind of have this memorized as one of the natural log facts, then we can just jump straight to an answer. I'll go ahead and write out the u substitution. So to integrate the left-hand side, I know that I have 1 over a linear term, dx. So I already know it's going to have something to do with natural log, but I'm going to get there by making u 3 minus 2x, which makes du negative 2 dx. And rearranging that, because I'm a little bit short on space, I'm going to go ahead and divide both sides by negative 2. So I'll have negative 1/2 over here, and I'll just erase it right there. That means that when I replace this, I'm going to end up with negative 1/2 and then 1 over u du. Integrating that, I'll have negative 1/2 natural log absolute value of u. And let's take this up here and plug back in what my u was. So I've got negative 1/2 natural log absolute value 3 minus 2x. Now we didn't integrate that right-hand side yet, but we'll do that really quick. When I integrate 1 dt, I end up with t. And we have to put a constant somewhere, and by convention, I'm going to choose to put the constant over here on the right-hand side. We have a choice at this point. We could go straight to trying to solve for the constant, but I'm going to rearrange this to make it say x equals first. There's a lot of algebra between here and making it say x equals. So slow me down and definitely let me know if I make any mistakes. I'll keep an eye on the chat. To deal with the negative 1/2 out here, I'm going to multiply both sides by negative 2. So I'll have natural log absolute value of 3 minus 2x is equal to negative 2t minus 2c. We have a choice, and we could at this point say, oh wait, negative 2 times a constant is just some other constant. Or we can drag around the negative 2c with us. Personally, I choose to make it a different constant. But because I know where we're going, I know we're going to end up collecting constants a couple of times. So I'm going to give this a subscript. So that's going to be C1. But now I'm going to collect this all up together and call negative 2C1. Nah, subscripts get messy. I changed my mind. I'm going with letters. So negative 2C, I'm just going to call that A. Now, I'm going to undo that natural log by raising both sides to be e raised to the something. So I'm going to have 3 minus 2x is equal to e to the negative 2t plus a. And again, I took the negative 2c and I turned it into an a. And there's a subtlety here, and we talked about it on Wednesday, and so did Professor Chaudhuri, where that absolute value really means that we could end up with the plus or minus version of that. But we take care of that by rewriting this right-hand side one more time and thinking about that as e to the negative 2t times e to the a. And then taking that e to the a and calling it yet another constant, because if I plugged that into the calculator, that would just be another constant, and I'll call that constant b. This b could take on a positive or negative value, and it's going to take on whichever value it needs to based on the initial condition. So 3 minus 2x is equal to b times e to the negative 2t. I'm going to pause here because there is a question in the chat that I don't want to ignore. It is personal choice whether you want to rename constants or just drag the same thing through your entire equation. By convention, most mathematicians, when they're writing this, will group constants at every step along the way. So, and by convention, we get rid of minus signs whenever we can. So when I have negative 2c, whether that's a negative 2 or a positive 2, either way, when I multiply it by a constant, it's still just a constant. So I'm taking the entire negative 2c and renaming that a new constant a. You could have renamed it the new constant negative a, and that also would have been fine. I knew that on the next step, I was going to get rid of it anyway and grab this whole thing and call it a new letter. So I didn't really worry about it. Next, if I'm going to get the x by itself, I could add 2x to both sides and subtract this whole thing from both sides so that I would end up with 3 minus b e to the negative 2t is equal to 2x. My last step, I'm going to divide both sides by 2. I don't know where else to put it, so I'm putting it up here. So when I divide both sides by 2, I'll have 3 over 2 minus b over 2 e to the negative 2t is equal to x. And then I'm going to do one last mathematician-y thing and take that negative b over 2 and call it my last and final constant, k. I'd go to c, but we used c at the beginning, so I needed a new letter. So I'm looking at 3 halves plus k e to the negative 2t is equal to x. And we haven't completely solved the problem yet because I still have to account for that initial condition. Well, if x of 0 is 1, then notation-wise, that's telling me when t equals 0, x equals 1. And I bet we can do this in our head. So when I plug in 0 for t, e to the 0 is 1. So this becomes 3 halves plus k is equal to x. Now I'm going to write it out. I was just trying to save myself a little board space. So that's going to be 3 halves plus k times 1 is equal to 1. And k is going to have to be negative 1/2. Yes, negative 1/2. 1 minus 3 halves, negative 1/2. So now that we have that value for k, my final answer is that x of t is equal to 3 halves minus 1/2 e to the negative 2t. That will be much better. Do you all want a chance to try this on your own, or do you want to just watch me do it? I'm good either way. Votes for who would like to try it on your own first. Like 3 people said they wanted to try it on their own. So I'm going to mute myself and give you 3 minutes to try this problem on your own to at least get started. And I will do a first couple of steps without talking. So if you're really not sure how to get started, you can watch me. But if you want to try it on your own, it's easier to tune me out. Okay. So to recap what I just did, but like push the fast forward button on it. Basically, I've got T's and Y's jumbled up in here. So I know that in the context of 17b, it must be separable if I'm supposed to solve it. If it's separable, I'm going to want to rewrite that y prime term as dy dt so that I can move all of my stuff with t's to the right-hand side and all the stuff with y's to the left-hand side. Well, after I did that, I got down to something that we're ready to take the antiderivatives of. On the left-hand side, to get the antiderivative of y to the -2, adding 1 to the exponent, dividing by the new exponent. He shows up a lot. So I'm going to go ahead and write it in the prettier form, or I don't know, maybe that's the wrong word to use. Mathematically, the form you're more likely to see in a textbook would go to -1 over y. On the right-hand side, helps to know your trig derivatives. Whose derivative is secant t times tangent t? Well, that's secant of t plus some constant. Now, if I'm going to get y by itself, I can multiply both sides by y and then divide both sides by all of this stuff. And when I do that, this is going to turn into y is equal to -1 over secant t plus c. Next, we're ready to deal with our initial condition. And again, notation-wise, this tells me when t is equal to 0, y is equal to 4. So I'm going to plug those in where they go. I will replace the y with a 4 and replace the t with a 0. And that's going to give me secant of 0 plus c. And I know that I keep throwing trig on here, and part of that is because trig keeps showing up in the web work homework. So I don't want to ignore it. But for sure, since you get that page of notes, if you don't feel comfortable with trig, I would make sure that you have a little box on your notes with some trig stuff, just as sort of a safety net. Because secant is 1 over cosine, my brain thinks a little better in terms of sines and cosines. And cosine of 0 is 1, which means 1 over 1 is also 1. And secant of 0 is 1. So I've got -1 divided by 1 plus c has to be equal to 4. I'll be honest, I am regretting at the moment that we didn't solve for c over here, because I think it would have been easier. But I'm here. And if I'm going to make this equal to 4, that's going to be some fun, messy algebra with fractions. We got this. So I'm looking at 4 is equal to -1 over 1 plus c. So I would multiply both sides by 1 plus c. So it's going to give me 4 times 1 plus c is equal to -1, or 1 plus c is equal to -1/4, which means c is equal to -5/4. A little bit gross, but not terrible. Which means that our final answer looks like this, but plugging in -5/4 for c. So I'm going to be lazy and just plug in -5/4 for c. Good times. So we've got these 2 strains of bacteria, and they're growing according to some differential equations. And we've been told that P is the frequency of strain 1. Well, so if I wanted to know, even if they hadn't given me the equation, I know I've got 2 different populations of bacteria, right? So I've got bacteria, that's the total of strain 1, and this is the number of bacteria that are strain 2. So if I were looking for the proportion, that's really what the P in my head stands for. It is the same as frequency. But if I'm looking for the proportion of all bacteria that are strain 1, well, that's going to be how many are in strain 1 divided by how many total bacteria there are. By the way, if I wanted to know what proportion are strain 2, well, the proportion that are strain 2 would look like how many of strain 2 there are divided by the total number of bacteria. Now, logically, if this is the proportion that belonged to strain 1, then the proportion that belonged to strain 2, if I think about this as like a percentage, if 30% are strain 1, then 70% are strain 2. If that's the entire known universe of bacterial strains, which means this term over here is equal to 1 minus P. And that's going to be important when you're doing part A and trying to show that the differential equation would work out to look like dp dt is equal to R1 minus R2 times P times 1 minus P. Now, this term here in the problem, they've given it a new letter and they've called it S. And one of the questions that you're asked is, can S be negative? Well, we don't have any constraints on the R1 and R2, right? But we do know that both strains are undergoing growth. So from the differential equation standpoint, I am expecting both of these numbers to be positive, but I don't know which of those numbers is bigger. So if R2 is bigger than R1, then for sure, this would end up being a negative number. And if R1 is bigger than R2, then this whole thing is going to be a positive number. So when we are looking at the equilibria and stability piece, it's going to depend on whether this term was positive or negative, meaning which of the two strains is growing at a faster rate. I said I was only going to spend 5 minutes on this. So the last thing that I'm going to say is, if you're struggling with how to graph this, your brain is probably better trained to think about what graphs look like if you use the letters X and Y. So I'm just going to replace the TBDT with Y, and I'm going to replace the P's with X's. And then I'm going to think about, well, what happens if I put a number out in front here? Just pick a number so you know what the graph looks like. If I pick a number, oh, that's a parabola. It's a concave down parabola because of the negative right there. It's got intercepts at 0 and 1. Cool. I don't actually need to know what number is out there, but I do need to know whether that number is positive or not. So when we had a positive term out there, or S was greater than 0, then your phase plot of dp dt versus P would look like this. If I had something like -3 times X times 1 minus X, well, this is no longer a concave down parabola. This one's concave up. I've got those same intercepts at 0 and 1. It's just that it's concave up this time when S is less than 0. Now, one thing to point out here, so for this graph, again, I'm kind of addressing the the equilibrium and stability piece here. So this is my phase plot, which means anytime the curve is above the axis, dp dt is greater than 0. So P is increasing, so my arrow should move to the right. And then anytime the curve is below the axis, dp dt is negative, which means P is decreasing, and I'm moving to the left. So this right here tells me that if S is greater than 0, then 1 is the stable equilibrium. Let's think about that in the context of the problem and why that makes sense. Well, if I come back up to what S means, S is telling me the difference in the growth rate. Well, if S is positive, then R1 is bigger. So strain 1 is growing at a faster rate. So what would we expect to see? Well, we would expect to see it winning. I would expect that strain 1 is going to win out, and the proportion of the strain 1 bacteria would get close to 1 or 100%. By contrast, over here, right, because remember the P corresponds to the proportion of strain 1 bacteria. And when I look over here, this is why I love phase plots. It's math telling a story. Okay, so over here, where the curve is below the axis, and I should have labeled my axes, that's P, that's dp dt. Where I'm below the axis, dp dt is negative, which means that P is decreasing, which means I'm moving to the left. So everywhere down here, we're moving to the left. And everywhere that the curve is above the axis, I would be moving to the right because P would be increasing. So when we're in this scenario, 0 is actually the stable equilibrium. And let's think about that. Well, 0, meaning the proportion of strain 1 goes to 0. Well, when S is negative, looking back at this, that would mean that R2 was bigger than R1. So strain 2 is growing at a faster rate. Well, if strain 2 is growing at a faster rate, it's going to beat out strain 1 eventually. So I would expect the proportion of strain 1 bacteria to go to 0. I hope that gives a little bit of context for problem 4. I will say that part A really just comes down to use the quotient rule and then do a whole lot of messy algebra. Equals mx plus b, or my favorite from 17a is usually the y minus y1 equals m times x minus x1. This is kind of my favorite from 17a. So I've got a point, the 1 and the 3. I can go ahead and plug those in and have y minus 3 is equal to m times x minus 1. And then I know that the way to get the slope is to take the derivative, because that's how I'm going to find the slope of the tangent line. So y prime would be negative 2x. And at the point where we care about it, we would be plugging in 1 for x. So I'd have y minus 3 is equal to negative 2 times x minus 1. And there are all kinds of ways that we could rearrange that. I could make that, y equals negative 2x minus a minus, so plus 2 plus a 3. So I could call that y equals negative 2x plus 5. And really, this would be a totally acceptable answer. And this would also be a totally acceptable answer. Okay, I just wanted everybody to be warmed up with equations of tangent lines, because Euler's method is all about using the idea of a tangent line to solve a differential equation, not algebraically, but to solve the equation graphically or numerically. I'm going to mostly erase this. Yes, I'm going to erase this. Oh, so there's a question of is there a preferred way to write the equation of a tangent line? Absolutely not. Both of these, and if you wanted to just start by finding the negative 2x and then plugging in the 3 and the 1 to solve for b, that's also fine. It really genuinely doesn't matter. Well, if this is the differential equation that I encountered, I would first look at it and say, okay, y is on top. So does it only have y? Nope. X is on the bottom. Does it only have x? Nope. Can I write this in some way that's like a function of x times a function of y? Nope. I got addition and subtraction and nothing that I can factor out. So this is not separable, it's not autonomous, and it's not pure time. So what do we do? Well, if this was a differential equations class, we'd have other methods to use. In the context of this class, the best thing that we can do is sort of approximate a solution. And section 7.3 gives us two ways to do that. We can approximate the solution by looking at a slope field and thinking about it graphically. And we can approximate a solution numerically by using what's called Euler's method. And that's what I want to talk about right now. So as a question, the question might be, use Euler's method and this initial condition to approximate y of 2. So what that's saying is if we know the value of y when t is, oh, actually, that's too many 2's. Let me go with a 3. if we know the value of y when x equals 1, can we use that to figure out where we're going to be when y equals 3? Now, I'm going to do just a super quick, rough, sketchy thing of what we're doing here, and then we'll go through the actual math. You might not want to take notes on this next piece. So the idea with Euler's method is I don't know what the curve y of x looks like. We can't solve to get a y of x. But I do have this one starting point. And I know, and actually I'm going to draw my lines a little bit more carefully and use my dots today. And say we're starting out at the point x equals 1, y equals 2. So I'm going to call that 1, and here's 2. Actually, no, I better make this, yeah, okay, we'll just go for that. That's the point 1, 2. That's where we've started. Well, what Euler's method says is we're going to start at that point. We don't know what the function is, but we could find the tangent line. And the tangent line gives us a linear approximation of the curve close to that point. So if I wanted to find the tangent line at that point, the other thing I would need to know is the slope. Well, the cool thing is the slope is just dy dx. And we have an equation to tell us what dy dx is. So dy dx at the point 1, 2 looks like 1 minus 2 plus 1. So far, are you with me? 1 minus, I'm plugging in, oh wait, I got that backwards. Supposed to plug in 1 for x. 1 minus 1 plus 2. Because I'm plugging in 1 for x and 2 for y. So at this point, my slope is 2. So if I started at this point and I moved with a slope of 2, or just a little bit, where would I be at? So the idea with Euler's method is that if we walk in little steps following the tangent line slope, we won't be exactly on the curve, but we'll be pretty close. So how small of a step? Usually we're told in the problem. I didn't tell us how small of a step to use in this problem, but I will now, and I'm going to say, let's use h equals 0.5. So I was standing at 1, and now I'm going to move over to an x value of 1.5. Well, how am I going to know what y value I'm at? We're going to follow the tangent line for a move of 0.5 in the x direction. So I started out at the point 1, 2. And if I'm going to follow the tangent line, then I need to go with that generic equation of a tangent line, which before I wrote as y minus y1 equals m times x minus x1. But I'm going to rearrange that to look more like our linear equation from 17a, or our linearization. So I'm going to move the y1 over. And I'm going to replace m with the derivative, which I'm just going to call y prime. And then I've got x minus x1. So this is what our linearization looks like. Well, we started at the point 2, 1. And when we plugged into the derivative equation at the point that we cared about at, our slope was 2. And the new, oh, I lied. We plugged in x1, and here's my x, and there's my y. Well, since I know the new x value I'm trying to be at is 1.5, the new y value that I'm trying to be at is going to look like 2 plus 2 times 1.5 minus 1, or 2 plus 2 times 0.5. So my new y value, when x is 1.5, my new y value is going to be 3. So now I'm at the point 1.5, comma 3. Then we do this all over again. And I say, well, I'm standing at the point 1.5, comma 3. What's my slope? And I come into this equation, and I don't want to erase anything, so I want to make sure I'm leaving it up there. But I come into this equation that dy dx, but I'm going to evaluate it at my new point, x equals 1.5, y equals 3. So my new slope looks like 1 minus 1.5 plus 3. So my new slope, that's a negative 0.5 plus 3, so 2.5. So I was standing at this point, and now I'm going to have an even steeper slope of 2.5, and I'm going to follow that slope another step over of 0.5 in the x direction to figure out what's the new point that I'm at. So I know the x value at this point will be 2, and I'm going to get the y value by using the equation. So my new y value is going to look like the y value I'm standing at, because I have a new tangent line. So the new y value I'm standing at is 3. My new slope that we just found is 2.5. And we kind of have a shortcut, because every time here, this x minus x1, we know we're moving in increments of 0.5. So I can go ahead and just plug in the 0.5 right here. Or if you prefer, you could write that as 2 minus 1.5. Can I do that math in my head? I think I can. So 2.5 is the same as 5 halves times another half. Would make that 5 halves times 1 half, 5 fourths. So that's 3 plus 5 fourths. 3 is 12 fourths. 17 fourths. Good times. So now I'm at the point 2, 17 fourths. And if all of that felt a little bit messy and gross, it was. But you know what? Computers are really good at doing this. So we're going to be asked to practice Euler's method by hand just to get a feel for what it is. But the truth is that in the real world, we would let computers do all of this iterative process for us. And in terms of questions that might come up on an exam to use Euler's method, we would generally only be asked to do sort of 2 steps like this, right? So we didn't actually get far enough to get to x equals 3. I'd have to do this 2 more times, but I'm out of time and I'm out of board space.